this class?
Yeah, it's right
Oh,
after.
yeah.
So you're gonna be pulling the doubles. You just
Mine's
sit
a
here.
minute. Just
Okay, let's see if this works. Does everyone have their laptop with them today? Oh my gosh, come on in. Yes. Josephine, anywhere. Who does not have their laptop with them today? Friends, yes. Friends. Do you have your laptop with you? Who does not have a laptop today? Anyone? You do not have a laptop. Do you have a laptop? Cool. Could we share maybe, because this is already looking like a clusterfuck of inoperability up here. So if you have your laptop, could you please open it up? We're just going to do kind of a cold intro, and then we'll do a soft landing, right? So I don't seem to have a working PC. Is this even on? No. It doesn't even, it's not even plugged in. Okay, is there a power strip? So please go to Jupiter with a Y, jupiter.org. On a browser, your favorite browser, I don't think it matters which one you get. Oh, here we go. Power strip. Why would someone do this to me? Okay, we have power. That's really good. Okay. Yeah, so go to Jupiter. This is looking good, and some of you probably have this already installed. But then go to, there's a couple links below. There's some little squares. I think we want the second one that says Jupyter Notebook. Am I correct? Down, just scroll down just a little bit. Are we seeing that? Don't go to installing. We just want, yeah, back up a little bit. That'll be your assignment. That's part of one of your assignments. But here we go. Yeah, Josephine has it. It says try in your browser. So click on the button that says try in your browser. Unless you already have it installed, and then open up a Jupyter Notebook.
That's an environment, yeah.
Yeah, so if you already have it, you're good to go. If you've got a weird environment set up, that might not get you the results I'm hoping you're going to get. Okay.
I just use the program browser.
So is everybody good
That's all my things.
on this? Anyone need some more time?
That's what mine is.
All right. Hey, I want to do some simple math. Let's start off. If we're going to do calculus in this class on our laptops in Python, so before that, let's just see how good we are at addition and subtraction. Just make sure, sanity checks. So could you please, so one of the cool things about Python, and is anyone never used Python in here? Cool, you're going to learn some Python. It's going to be great. You're going to be able to put it on your resume by the end of this class. It's good. It's going to be killer. So you have this little command window, and up at the top you'll see some buttons, and one of the buttons looks like a play button on some kind of music device or something like that. So what I'd like you to do in here, you can use this just like a calculator. So in here, just type 9.99975, so 3 9s, minus 9.99925. And tell me what you get, and tell me what we should get. What, if we were doing this without our computers, what would this actually equal? And I hope we can do that. We might need to change the prereqs. What should this be? Somebody help me out here? Here, I'll start. 9 minus 9 is 0. What's the rest?
0, 0.
3 zeros and 5, and then a 0, just to indicate that we actually had precision out that far and let everybody know. So put it like that. Did you get that? You did not. No, it's not right. Okay, maybe it's just these numbers. Let's try different numbers. Now, in the new one that's appeared, or you can alter this one, Or you can even go up here, hit enter, and it'll make a second command line under that, and you can enter this as well. 0.99975 minus 0.99925. So same thing, except there's a 0 in the ones digit. And what should we get? And I didn't start recording. Did I? Maybe I did. Oh, look at me, I'm really on it. What should I get? Truth, true value. No calculators.
The same value.
Same thing, thank you. Good, good. All right, we got to get a little more pepped up. I'll start bringing some sort of coffee or something, coffee tablets. We could take, what, did these turn out the same?
No.
They are not the same, are they?
No.
These are both wrong, and they're not even wrong in the same way. Please notice that. We want to send a rocket to the moon, to Mars. We can't even subtract? Weird. Okay, let's try another one. Oh, so it's probably just subtraction and weird canceling stuff. Let's try a new experiment. So in a new command line, I'd like you to enter left paren, 0.1 plus 0.2, right paren. So using associativity, we're associating these two, doing that first, plus 0.3. Please try that. What should I get? What do we get? What's the truth? 0.6 should be the answer. Do we get that? What do you get?
0.0000001.
It's pretty damn close, right? But then there's, what was your last digit here? Was it a 1 or a 4?
I got a 1.
Got a 1, cool. That ain't right. It's close. It's close. A lot of zeros there, pretty close. But if we're dealing in trillions, and this represents trillions, that's not very good. Let's try it again. Let's try 0.1, not in the parens, and let's group the 2.2 plus 0.3. So 0.1 plus left paren, 0.2 plus 0.3, right paren. You got a laptop though, right, Christian? What's up? You do have one. Okay, awesome. If not, I'll hook you up. How did this work?
That looks pretty right.
Oh my God, we did a simple computation correctly. We actually got 0.6. Bravo, Python. Bravo. 3 numbers added together. So we've got this language in front of us, this very mathy language. Thank you. I appreciate the effort. We've got this very mathy language, my favorite programming language. I was trained as a mathematician, and then I got a job at IBM and had to learn C programming on the fly. I liked C because everything was just, if you're a CS person, top down. So I could just write, do this and then do this and then do this. I don't know anything about object-oriented programming, which is Java and things like that, and classes and inheritance. I know almost nothing about that. But I do know a lot about this because it's just how my brain works as a mathy nerd person. Python works exactly the same way. We can do beautiful just flows of computation that makes sense to the mathy linearity that we kind of crave for at times. We also crave for non-linearity at times, but so what is going on here? We're going to get to that in a minute. I want to talk about the nuts and bolts of the class first, and then we're going to spend today and Wednesday talking about why is this happening, and you are going to understand this at a level you've maybe never understood it at. Even my CS friends out there, and I know there's many, how many of you had to do conversion to this format, or does this look familiar? Does this look familiar to many of my CS friends? Yes! You got something new coming up. So, this is the format in which numbers are stored in all digital computers, and it was revised back in 2008. That's the most recent update that I know of. This is why we're having problems. But it's not the fault of this, it's the fault of infinite things being crammed into a finite device. You're gonna suffer somewhere. You're gonna lose something when you've got everything in the world and you want to put it in a box. So, we're gonna get into this, but first let's get to some assignments that I have for you, and these should all be in our World Class page. World Class. So maybe you want to look at it real quick. Could you please just pop in there, and Christian can ride along. Shotgun. You know. Oh, I actually have a laptop now. This is good. Might not even need it today. So if we go to World Class, look at the assignments, which should show up on the right. You have 3 things you need to do for me by like the end of next week. So the simplest thing is install using Anaconda, and I've got a video in there. This is just a manager for all sorts of programming packages, and you install this on your laptop or your home device or both, and it will by default install the Jupyter Notebook. That's part of it. It will also install the package. There's all these different packages of routines. The one we're going to be most interested in is called NumPy, but it's probably NumPy because of Python. It means numerical Python. So this will come along with all this. So what I would like you to do is by Wednesday, I think that's the due date, by the end of Wednesday, show me you have this installed. Or just tell me. If you lie, that's weird, and that's on you. Yes.
I have Numerical installed without counting. It's the same thing, but in a
Cool. Honestly, yeah. And if you might have other ways of getting this. I don't care if it's Anaconda, Daniel. So as long as you got access to Jupyter Notebooks, we're good.
Okay.
Yeah. Any other questions on that assignment? Pretty chill. By Wednesday, please send me an email confirmation letting me know that's done. Do send email, don't tell me after class because I'm not going to remember. And then I would like you to all, even if you do have this experience in programming in Python, this will be easy. If you already know Python, you'll probably knock this out in like an hour. If you don't, if you've never used Python or any programming language, there is a roughly 4-hour boot camp to get you up to speed. I would like us to try to have this done by the end of next week, because then we're going to start coding and stuff. We will be taking mathematical ideas and writing code to implement them. Don't get stressed about that, because I don't expect you to be a programmer. This isn't a programming class. I just want you to know something. I'll probably give you lots of the code and we'll hack it. So if any of this stresses you out, just talk to me and we'll make sure that that I'm holding you carefully and gently, and we'll get you through this. You can do this. So this is due the end of next week, and then there's one new assignment that will come up, and we're going to start talking about that. I believe it's called Binary Basics. Is there an assignment up with such a thing? Cool. So that's got 5 problems on it, and this I would like by next Wednesday. We'll start there. If everyone who's in here who's had me before knows that if I set a deadline and we're looking at it like going, can we have more time? You can have more time, right? So I'm pretty flexible. I'm not tyrannical about anything. This will be written up. You can type it, you can do LaTeX, you can handwrite it, but this is a hand-done exercise. All right. We good? Any questions at all? Ava, are you going to be able to see with that thing? Sometimes you're not going to be able to.
I mean, I can see the board.
Okay, sweet.
And if
Okay.
it's a problem, like, on next time we have this class, I can not sit here. So, we can figure it out.
You seem like you're going to sail through life with no effort. You got it figured out. All right. I need help finding my eraser. Right there. Cool. Thank you. Need to get a tracker on it. We'll get one with one of the iPad, the little Apple trackers, and put it inside. Okay, so fun stuff for you to do. Some of you might have already done it. Who has watched Paperclip Computer, or at least read what I posted in there? Anybody watched it? Vivian, I saw you in early. I was thinking, Vivian's in there watching it.
No.
Okay, you were okay. That's cool. Okay, fair enough.
I read it though. So.
Yeah, cool. So I'll tell this story for those who haven't read it. When I was 12, I really wanted an Apple II computer. I was a nerd. We're all nerds, right? Like, this is cool. I can talk about this. I can say nerd because I am one. Geek. I was kind of a loser. That's how I felt back then. But we now rule the world. Even though we felt ostracized perhaps in our youth, we have all the power. So, I didn't know that at the time. I just wanted an Apple II computer, but our family was kind of poor. They were like $700 for the basic model. Came with like 17K RAM. Boy, it seemed sweet. They were just so beautiful, those original Apple IIs. So we couldn't afford it, so I would go down to the local computer store. I'd ride my bike down, and they had this rack of books with all these programming books, just books filled with code for the enterprising nerd to get and enter into their computer. There wasn't a lot of software available. You had to actually do a lot of it yourself. So there was this one called more basic computer games, and this was just literally books of code, more or less debugged, not always. But it had cool games in it like Hunt the Wumpus. Y'all know what I'm talking. You ever heard this one? No, it's like, it says, you hear a sound to the north. Which way do you want to go? And you had north, south, east, west, whatever. And you just move around, and you had to avoid this wumpus. And it was just really all in your head. It was a maze game. If you had an actual maze game, man, that was like high-res graphics, if you could see the maze. So, I found another book there. It's like, I'm never gonna get that computer. But the book that I did find was this, How to Build a Working, I like that, it's gonna work, working digital, oh, I like that even more, digital computer. And please go to announcements and look at the cover. I think it's there. Yeah, there it is. Check out that cover. Notice that is plywood and paper clips with screws holding the paper clips to the plywood. So I thought, okay, let's go for it. So I started trying to build this computer that was in there, but I kind of lost steam after building just one very small part of it, never completed it. Ended up getting, luckily, a VIC-20 computer. Ever heard of that one? Came before the Commodore 64. You heard that one? Maybe that one? Yeah, you can still get emulators and stuff for these. This VIC-20 had 22 columns of text you could type. 22 characters across, that was it. It was really weird, they were really big and odd. But I loved programming. I spent so much time, spent all my time working with these things. And later on, found someone who had built this. So please just have the fun. And not right now, but I've got a video on there of this dude who built this recently. So you can go see the video. He's got all the plywood in there, the light bulbs, the switches, the throw switches that you threw by hand. In this computer, you're the CPU. So he actually does this. I think he does this problem, 7 minus 4, using that computer. Now we know the answer, right? 2, no, just kidding. All right, it's 3. It's 2 in Python because of rounding error. I'm just kidding. So he does this, and it takes like 15-20 minutes because the first thing he has to do is enter the numbers, and this is where we're going to pick up the lesson for today. So he has to take the number 7 and convert it into a format the computer can handle. So this is decimal. This is our number system that you do everything in unless you're a computer person. We have this thing called the decimal point, and it separates the whole from the fractional. And it does it in a very precise way in particular. It's got 10 to the negative first here, so those are our tenths. We've got 10 to the negative second here, those are hundredths, and so on. For smaller and smaller fractional parts, here we have 10 to the 0, 10 to the first, 10 squared, so this is 1, tens and hundreds place. This should not be anything new. You just probably haven't thought about it in a while. But it's good to think about how this system works. Because when I write a number like this, I understand it intuitively. I know that it's an approximation for pi. But I rarely actually think, well, this means there's 3 of these ones. There are 1 of these tenths. There are 4 of these hundredths, and so on. So this thing is actually 3 plus 1 times a tenth plus 4 times 100 plus 1 times 1,000, and so on. The thing about computers is they're electronic devices. At least the new ones. There's old analog computers that aren't electrical at all. They got like wheels and stuff like that on them. But for us, our computers all operate on switches. So those paper clips you see on that board, there's a little board, and it's got some paper clips screwed down to it. So there's a paper clip kind of screwed down. What the hell could I do with that? Well, I could clip it to some other wire. So let's say there's another wire coming like that. I could connect that paper clip to that wire so that I make a connection. Here's maybe some current flowing, and I connect this and I complete the circuit. I make a continuous line across here. That would be on, or I separate them, and then that's off. But that's all I have is on and off with a computer. And it's all hidden inside there. At the deepest level, a computer is really fancy switches, microscopic switches, doing all sorts of stuff. So that's part of the hint as to why our numbers weren't working out before. So the computers that we work with and computer science all works around what's called binary. This was decimal. We're going to work with binary for the next week or so. And this is base 2 as opposed to base 10 up here. So my places are going to look like this. Not a decimal point, it's called a binary point. And here again is the fractional, and here's the whole, and we do the same rhythm. My base is 2, so it's 2 to the 0, 2 to the first, 2 squared, 2 cubed, on down. So this is 1, 2, 4, 8, 16, 32, 64. And then the fractional stuff is 2 to the negative first, 1/2, 2 to the negative second, 1/4, and on down the line. So now if I wrote in binary this number, and we're going to use a specific kind of notation, I'm going to use these parentheses with a little sub the base down here. This tells me what I've written here is in base 2. So if I write, for example, 101, and then I put 0011, notice there's no digits other than 0 and 1. That's all I got, off or on. So this is 1 here, 0 here, and 1 here, which means I've got a 1 plus, I wrote that backwards. 1 here, 0 here, 1 here, and then 0, 0, 1, 1, like that. So I've got 1, 1, no 2s, and 1, 4. So this thing here is actually 5. Does that kind of make some sense, vaguely? Yeah? And if not, we'll work on it, and I'm going to do some more examples. Over here, I've got no halves. I've got no fourths. The next one would be an eighth. and then the next one would be a 16th. So I've got 0 of those, 0 of those, 1 of those, and 1 of those. I'm sorry if this is review for some of you, but kind of brand newish for most folks. So this over here is 1/8 plus 1/16, and gosh, I'm not good with that. Could somebody do that on a calculator for me? It's 3/16, so it's 5 3/16, and what is 3/16 in decimal form?
0.1875.
Okay, thank you. So this number here in base 10 has this representation inside the computer. So now I can take this number that required 10 different digits and store it in the computer by going to a piece of memory that's allocated for such things and flipping the switches on or off to mimic this, roughly. But in a more detailed way, that's what IEEE 754 format is about. How do we take this and turn it into that? All right, let me stop. Any questions on any of this, friends? No? Good? Okay, cool. All right, so let's talk more about binary. I want to show you how to do this by hand. There are tools on the web. There are tools on the web to do, well, everything we're doing this class. AI can write every piece of code I ever ask you to write. No?
It makes a lot of mistakes.
It does, but it can get you rolling for sure. Yeah. Sometimes it can catch your mistakes too, right? Yeah. So we want to have an understanding. We don't want to convince our bosses we're not needed, right? So we definitely never want to say the computer is perfect and never makes mistakes. So I want to be able to do this stuff by hand. Let me show you how to convert from decimal whole to binary whole. This is a fun little algorithm. It's good to know algorithms. It's good for your brain. Is anybody here going to teach ever? No teach. Maybe. Yeah. This is just a really cool thing to teach. You can all teach this to anyone. This is just freaking awesome. So let's say I want to convert 7 in base 10, and I want to convert that to its base 2 equivalent. That's a whole number, so I'll use this scheme. So I write 7 here. So I initialize the algorithm by just writing the number down. And then I start dividing by 2. So the algorithm is divide by 2, record the remainder. That's it. So I divide this by 2. 2 goes in, so let's see, we divide by 2. 2 goes in 3 times, and there's a remainder of 1, because that's an odd number. So let's keep track of the remainders over here. Remainder of 1. You might organize this differently, but this is kind of how I do it. Now I divide by 2 again. 2 goes into there 1 time. I have a remainder of 1. Divide by 2 again. Well, I can't divide by 2 again. So the way I do this now is once I get to 1, stop at 1. Can't divide it by 2 wholly. So now all I do is read this backwards. So this is step 1. Step 2, step 3 is read this backwards. And so what I'm going to do is write 1, 1, 1, and that is my base 2 conversion of 7. We can double check this. Let's double check it since this is new for some of us. This is the 1's position, the 2's position, and the 4's position. I have a 4, a 2, and a 1. Gives me 7. Sound all right? Could you do one real quick for me? Let's try one together. Do a quick conversion. Yeah, you've been sitting around listening to me blab for about a half an hour. I appreciate you. But what I would like you to do is convert to base 2. So let's do 173 in base 10. What does that look like in base 2? Let's give it a shot. Just soothing algorithms to start off the school year. what you do in numerical methods. We learn to divide by 2 today. Practiced it a lot. Your last place will always be a 1. Because if you're starting with 0, it was something that didn't need to be written. You never write leading digits that are 0. Check me out, am I doing? So we got 1, 1, 0, 1, 1, 0, 1. Did I do that right? That's good. That would be a bad first start. So check it out, take your time. Let's make sure everybody's coming along. If anybody falls off the wagon, we go back and pick them up. Or get them an Uber. So on the homework that I've given you, the binary basics, I would like you to do it by hand, please. It's simple, it's soothing. You can check yourself on a billion different base converters available on the web. Let me know if there's any troubles with this, any questions. You might screw it up at first because you forgot like how many 2's go into something. That happens. It can be a little stressful for me. It was here. I wasn't sure about that 86. I don't know. Or the 73 was a tough one. Christian, you doing good? You doing okay? Does anybody need clarification on this? Because I kind of want to go to the fractional part. So let's, yes, Thomas.
I guess, so when you get to 2, do you just stop there?
Yeah, as soon as you get to 2, you're just going to put a 1 underneath it, and then you're done. Yeah, as soon as you've gotten to 2, the next step is your first digit, which will always be a 1.
Okay.
Or maybe 3 is your digit there, but you'll always end up with a 1. Okay, so let's do converting a fractional decimal. This one's really fun. And oh my God, who's helped me with the origami at Scholarship Weekend? Does anybody help me with this, the binary, using origami to do this conversion? I kind of feel like we need to do it. Like I think we're gonna have to do it in here because it's too freaking cool to use origami to do what we're about to do, but we'll just roll with it. Without paper for today, to fractional, convert a fractional decimal to a fractional binary. All right, so let's start off with something pretty straightforward. Let's see, when I did that last conversion, what was the little decimal part at the end? It was 0.1875, cool. So let's do something we know the answer to. So I'm gonna take that, that's a base 10 number. I would know it's not base 2 because there's numbers above 1 in it, right? So instantly I know that. I'm not sure what the base is, it still could be base 9, but that would be a weird world to live in with base 9. All right, so here's the plan, and it's just easier to show you these things than it is to write it out. So the first thing is write down the number you want to convert. And then we're going to multiply by 2. So instead of the dividing by 2 on the whole side, we're going to multiply by 2 on the fractional side. And this is pretty straightforward too. You just have to be able to do the multiplication by 2. So you might need a calculator for that. This is a kind of a sucky one. Let's see, what is that going to be times 2? So 0, 5, 7. Is that, help me out, is that?
That's what I got.
That's what you got, cool, I'm gonna go with that, that sounds good. So what we then look at is watch this leading number. Because this is going to be where we get our encoding from. The digits that pop out in front are going to give us our binary. So let's watch out in front. Just make a note of it. It's a 0. So that means that in my binary expansion, the first digit is 0. So if I come over here and I do my base 2, I'll put that there, put a 0 point, because this thing's fractional, there's a 0 in front, so there's no wholeness. I'm going to put 0 here, so that goes right there. And then I multiply by 2 again. So as we do that, then we've got, let's see, we're going to get extra 5, 5, and then 5. Help me out. How do I multiply by, is this 7?
Yeah.
Is that right, what I just did? Yes, no. Yeah. Yeah, thanks, Lou. Thanks for having my back. So this now is the second digit. There's a 0 out in front. So that becomes the second digit. Now things are going to get interesting because when I multiply by 2 the next time, I'm going to get a 1 out in front, right? So when we do that, we're going to get 1.5. Is that right? Yeah, 1.5. So I have a 1 out in front. So 1 becomes my next digit. And that means that I just write it over there. When you get a 1, toss it away. Record the 1. So record 1s, then send them to 0. Then replace with 0. So I'm actually going to have this little kind of side step here where I'm not going to multiply by 2 yet. I'm going to first rewrite this as that number. So I just stripped off the 1. And now I'll multiply by 2 again. So now when I multiply by 2 again, let's see, I got 3 multiplied by 2. I'm going to get 1.000. I record the 1. That's my last digit. And there's no more fractional stuff. So I'm done. So there's no more fractional stuff. Done. And now I have my conversion. And this is right, because we went the other direction, right? This was the binary number we had. We converted it to decimal and we found out it was this. So we know that we got it right. All right. Your turn, and then we'll find out if you have questions. So, let's see. Yeah, we'll try this one. I've got tons of examples of this up near your assignment. So near that assignment or in content, if you go back into the content area, look under binary basics, there's videos, there's examples I've written out of how to do all of what we're doing today. So, your turn. Convert, please, 0.11111111, repeating forever and ever, to binary. This is base 10. Now that's what a tricky man. Those are base 10 ones, not base 2 ones. So start with this number, and you can just keep it on. And you're going to discover something cool. So just keep multiplying by 2 until you get a 1 out in front. might be short one. These are just examples you can take home. I think these are also posted up there. This has got more than we've done on it. Actually, Lou, could you pass these? Could you just pass these down? Thank you. All right, that's it. We're gonna have to get the rest. They'll come. They're on their way. Hopefully. Hi. Ooh, cool. Thank you. Labina, I thought I'd never see you again. It's great to have you here.
Great to be back.
Yeah. Outstanding. What is this number in fractional, in like decimal fractions, base 10 fractions? Do you know? It's 1/9. So this is actually 1/9. We use fraction notation converted to a repeating decimal. Now we're going to figure out what that is in the computer. So when you tell your computer, hey, I've got 1/9, I want to work with it, what is it going to do? This is the first part of that process. So we got this. So just repeat it. With 3 zeros at the start.
3 zeros and just keeps going.
Record also 0.
That's quite the trick.
Isn't that cool? I think this is just like one of my favorite things to do. I hope this isn't confusing. I'm just grabbing those from over there and showing what I'm grabbing there. And then the third one, do times 2 again. We get 0.8. So again, I've got a 0 as my third digit. And then, now we get finally a 1 when I do this. So the fourth digit is going to be a 1. But what do these, is that 6s? Or what is this, when you multiply that by 2, what do you get?
7s.
7s. Okay, that makes sense. It's kind of cool, actually, too. That's, okay, cool. So I record this 1. I remove that 1, so I kind of send this to this number here. And then we multiply by 2 again, and we're going to get 1.5s. Yeah. On down, so I record the 1, strip it. So let's put that here. So 6 digits gonna, well, we got this. Now I multiply by 2 again. And what do I get? All 1s. Cool. So my next digit, so did I record this guy? Let's see, I've got 3, this is 4, this is 5. Okay, and my last digit then is going to be this 1, because as soon as I strip this, my last digit that I need to think about, as soon as I stripped this first 1 off, I'm back to where I started. Do you see that? That like we're back to the beginning, and we know how that rolls. So that means we have a repeating decimal, and this just keeps cranking. Then we have 3 zeros, 2 1s, 3 zeros, 2 1s, on and on and on. Now we have the infinite binary fractional expansion. Did I get that right?
You drop 1.
Did I drop a 1? What did I?
It's the last one.
3 1s.
Yeah.
Wait, so I got a 1 and a 1. Should only have 2 1s, right?
That's
Yeah,
true.
sure.
Go back
Right.
to Because then when you multiply it by 2, you get.
Oh, this guy here.
Yeah.
Yeah, okay, yep, yes, sorry, I did forget. Yes, I should have recorded that. Now I'm back. Thank you. 1, 1, 1. So it's 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1 ad infinitum. So we could actually do it with that classic kind of grade school notation of that. Okay, yeah, and you get to practice some of this. So now, step 1, the computer, I tell the computer, I need to put 1/9, do something with 1/9. So I say, I give it a variable and I say a equals 1 divided by 9. First thing it does is it converts it into this form. Second thing it does is it starts this process, not with this algorithm. It's got its own ways and very speedy methods for doing this. But then it understands that the number 1/9 is this, but it can't see infinity. It can't see forever. Computers only have a finite number of switches. So let's talk about that. The more switches you have available, the more accurate and precise you can be. And the fewer, the less. So, let's talk about precision. There's really only two. There's really only one we'll need to work with, but there's two that we're going to think about. So the first thing is single precision. And what this means is that our computer allows 16 ones or zeros to express a number. So I've got here the first bit, this will be my sign. If it's 0, the number is positive. If it's 1, the number is negative. So I flip that switch on if it's a negative number. The next digits here, there are 8 of those. So here we have 8 bits. A bit is just a binary place. So I have 8 bits here. This is for the exponent. That's 1-bit sign. Here I have the exponent. That's got some subtleties to it. And then here is what's called the mantissa. And this is the significant stuff. This is the details of the number. And all we have here is, let's see, we got 1 plus 8, that's 9. We're only allowed 32 spots here. So that means this mantissa is 23 bits. So I have to take every number that I want to deal with and somehow find the right zeros and ones and plunk them in here. Let me explain what this exponent is, because it's kind of weird. So this exponent here means that we've got the mantissa, and this is slightly altered, but we have it times 2 to the exponent power. So this exponent here is that number there. And think about scientific notation. So if I had 2.3 times 10 to the 5th, scientific notation, you know that that means take this decimal point and shift it 5 places to the right, and you know that that means this number. Well, in binary, we're going to do this exponential notation. So for example, if I have 1.01 times 2 to the 3rd, this is just the shifts. If it's positive, shift right. If it's negative, you shift left. So this becomes, and this is base 2. This is base 2. This is equal to 1.01, but then I shift 3 places. 1, 2, 3. So it's actually this number right here, which is 10. This is equal to 10 in base 10. I've got 1A, 1, 2. So what we're going to do then is take this number, write it like this, and then use that for this encoding. So this is on the path to IEEE 754. So the best way to do this, honestly, is with an example. several examples, but let's talk about double precision really quick. So double precision, which is exactly what's happening there right now. The default for Python 3 is double precision. And for this, we've actually got 64 bits. So here we have 32 bits. This is 64 bits, twice as many. We still have this first bit, single bit for sign. So you have a sign bit. 1 is negative, 0 is positive. Then here I've got, wait, I know that this is 52 over here. So I have to, 52 plus 53. 7. Shit, I think it's 11. Yeah, okay, it's 11 bits. So this is 11 bits for the exponent. So I have 1 here, that's 12, so over here, 52. Okay, so this is your mantis. So this is 52 bits. All right, let's do an example. Full example of this whole thing. And let's in fact do it with, why not just do it with 1/9? I'm going to convert this into single precision IEEE. So, problem. Convert 1/9 in base 10 to single precision. That's what you need to do. IEEE 754. Step 1, convert it to a perfect binary representation. We did that. Step 1, convert to binary. And keep all the accuracy. You want all the information here. So we did that. This is 0. I'm going to write it out in its not shorthanded way. So we did that. So that's a 9. Step 2. Shift this number until a 1 is the leading whole number. So I'm going to kind of go for scientific notation, but in binary. So we're going to shift and write in exponential form. And I apologize for those who aren't used to my scribblings. If anything is not clear, I will help you. Just let me know, please. Shifting right in exponential form. So that means I'm going to move this decimal place from here to here. So I've got 1.110011001111. But this isn't the number. I actually want to move that. So if the decimal place is here, we need to move it 1, 2, 3, 4 to the left. So I put 2 to the -4th. So this negative means shift left. Negative exponent equals left shift. And here it's by 4 places. So now I've got it in exponential form. And there's like dots here, right? Keep on cruising. All right. Just about done. We're going to do this with every single number. When I worked at IBM, so if you don't know much about my history, I spent like 7 years of hell programming at IBM. It was like the darkest period of my life. Just fucking terrible. It's just, I hated every second of it. They didn't like me, I don't think. Maybe it was the vibes I was putting off, I don't know. I don't even know where I was going with that story. What was I saying? I hate IBM, I don't know. Oh, one of the things I did learn to appreciate there were these algorithms, like the one we're about to see, and just the thought, all the different thoughts that go into making these standards. One of the things I actually was an expert in for a while was in JPEG format. I worked in a research area. We were trying to find high-speed image processing algorithms. So I know a lot about JPEG, and oh my God, maybe sometime I should do a little talk on this because it's so freaking amazing. There's not just computer science, but there's physics and physiology and the nature of the human eye. Like they took all that stuff into account and made one of the great inventions of all time. It kind of made the web possible in the early days. So JPEG's really cool. IEEE 754, also freaking cool standard. So once we've got this, really the hard work is done. Now we're going to encode into 32-bit IEEE. So the way I do this is I lay the bits down, and there's one little caveat, and this is the thing I'm thinking of that I haven't said yet on how we do this. So first off, I'm gonna truly make 32 slots here. So there's 2, there's 4, there's 8, I'm sorry, there's 16, and then one more. I should be at 32, awesome. Got me 32 bits right there. Fun. Little fence that I have up there. I don't like this bottom of the fence. Let me fix it up. Okay, so easiest part of all is the sign. This is a positive number, so the sign is 0. I plunk a 0 in there. And then I have 8 bits. The next 8 bits are the binary representation of the exponent. So wait, 1, 2, 3, 4, 5, 6, 7, 8. Now, I'm not going to enter -4 because the computer doesn't know what -4 is. It only knows 0s and 1s and all the numbers here. So this thing right here, let's kind of pull this out into a little zoom in. Let's zoom in to just that 8-bit section right there. So this is 2, 4, 6, 7, 8. I have to encode my exponent into here. So what are the range of numbers that this could represent? Hey, CS friends, or folks more binary associated, what whole numbers can I represent here if I use 0s and 1s?
I think it's 0 to 65,300 something.
That's little bits, not that big. That's for more bits, definitely. That's the That's 16 bits. That's great.
200.
What?
0 to 256.
And 255. Yep, exactly. We've got 256 values. So does that, because the 255 is when they're all 1s in there, and then 256 is if I had a spot right here, this is the 256 slot, 2 to the 9th, 2 to the 8th. So the range is just this, but I've got a -4. Yikes, that doesn't sound good. So how do we do this? Well, we kind of take this range from 0 to 255. Those are all the possible things we can encode in there. And we split this in half roughly. And we allocate half of this to positive exponents and the other half to negative exponents. So this is the encoded number, but what it represents is some different exponent with 128 added to it. So this is the encoded number, this is the desired exponent. I'm going to put in this column right here. So 0 gets encoded as 128. So what you do is you just add 128 to your desired exponent. So what I'm going to encode is 128 minus 4, so 124. But that means we've got some problems here. This means our lowest exponent would be -128. And our highest exponent would be 127. So this is the largest exponent, and this is the lowest. And those actually end up having special values to themselves. This is going to turn out to basically be our 0, and this is going to turn out to be our infinity. But let's worry about the basics first. That's just little cases. So, step 3, convert. So step 3, encode sign bit. 0 or 1, positive or negative. Step 4 is encode the exponent. So add 128 and then convert to binary. So our desired exponent will be 124. Get rid of this stuff here. Tell me if this is making sense. Let me stop. Do you see where I got 124 from? 128 minus 4, oh man. Absolutely. So got that -4 exponent on the number I want to encode. I added 128 to that and I got 124. So that's just 128 plus -4. Yes, ma'am.
So if we had like -7 up there, it would just be 128 minus 7.
Correct.
And if it's positive something, it would be 128 plus that.
100%. If this were 2 squared, because I wanted to shift 2 to the right, then it would be 130. Oh, so you take this, you add 128 to it, that's what you need to encode. Hey, little quick practice, can you encode that in binary right now? Divide by 2, divide by 2, divide by 2. Let's do that, let's practice that. That's base 10. What is it in base 2? So, okay, I'll stop here for a second. Check me out on this. Are we agreeing that 124 in base 10 converts to 111, 1100? And if not, let's figure out what happened. Please ask questions. Please always play along in class, because if you by the end of class you'll know how to do everything. You'll be an expert. And what's the point of being here, right? Otherwise, not having fun. Any problems with this? How many bits are here? 7. How many do I need? 8. What is missing? What should I do to remedy the situation?
You just stop at 0.
I have a leading 0. So here we have 7 bits, but need 8. So we have a leading 0. This number out here, think about the bit spots. This is 128, this is 64, 32, 16, 8, 4, 2, and 1. So to get any number less than 128, we just need these spots. As soon as the number's 128 or 4 or more, then I'll have a 1 here. Notice that numbers 128 or more are the non-negatives. So the non-negatives are going to have that 1 in the front of the exponent. So for this, I'm just going to encode 0, 1, 1, 1, 1, 1, 0, 0, just because I want 8 bits. So leading 0. And I put that over here then. And so then this is going to be 0, 1, there's 5 ones, and then 2 zeros. Cool. Got the first part encoded. That's really about the hardest part. We got one little bit more to do. So this mantissa always assumes that we have taken our number. We've taken a non-zero number. If the number's 0, we're just going to do something particular. But if the number's non-zero, I can always write it as 1 point stuff times 2 to some power. So we'll always be able to get this 1 out in front. So why encode it? So this is one of the cool things about a standard like this. They were like, well, look, man, we only got 32 bits. Why waste recording that when we know there's a 1 there? So we say, assume there's a 1, and then start recording after this stuff. So this, we record after the first 1. So the fractional part of that mantissa, of this significant portion here, we just record the stuff. Stuff only. So here, let's go back to our number. Let's see, where do we go? Here he is. Got a beautiful rhythm. This shouldn't be too hard. So I'm going to encode 1, 1, knowing that I've got this unspoken 1 point in front of it. So I've got 1, 1, then 3 zeros, and then 3 1s, and then 3 zeros. I can stop looking at it, and then 3 1s, and then 3 zeros, and then 3 1s, and then 3 zeros. But uh-oh, kind of missing some stuff, right? Because what would come right after this is 1, 1, 1, 0, 0, 0. This is lost over here. So we're going to round. We're going to round. We're going to look at this part that's over here. If it starts with a 1 and then stuff, or actually if this starts with a 1 over here, I'm going to round this digit up to 1. And it does, so I'm going to round that digit up to 1. If this over here were starting with a 0, I would round down to 0. So here, we're going to round this up to 1, right here. So round up last digit to 1, because the remainder, the lost stuff, starts with 1. That's it. If the lost stuff starts with 0, just keep a 0 there. Or don't do anything. Leave it as it is. Okay. We're done. Got one last thing. Time is cool. Got 5 or 6 minutes. Perfect. Last step. Did you have a question, Lou? Cool. Any questions on getting that? Last step. Look at the example I gave you. It's written in hexadecimal. Base 16. If you ever take a computer and you do a memory dump on it, if you were to look at just some memory, sometimes you'll see programmers filling it up with like words like beef. You will often see beef as a memory fill, at least you used to. And maybe, I think actually dead beef was the one I saw a lot. They're filling up memories with these letters. These letters are just representations of bit patterns. So let's talk about the conversion to hexadecimal. Hexadecimal is base 16, and it's a very nice way to compactify base 2 stuff. So, last thing, base 16 is called hexadecimal. And we see this all over the place, we just don't really think about it much at all. So what we have here in our places, this is the hexa point. These are the fractional parts. This is the whole parts. So over here I've got 16 to the 0, 16 to the first, 16 squared. On up here I've got 16 to the -1, 16 to the -2, 1 down. We're only gonna worry about this part. This is our concern. Our concern is whole hexadecimal numbers. Let's call it hexes for now. Really straightforward way to think about hexadecimals. So we started, here's our digits. These are the digits of hexadecimal. You gotta move past 9 somehow. So we started 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we need a 10, so we call it A. We need an 11, we call it B. We need a 12, that's C. 13, 14, 15. So this represents 15. That represents 0. That represents 10. And so, for example, if I gave you a hexadecimal number and I said, hey, what's this? AB in base 16. Well, what that means is that I've got an A in the 16 slot. So we've got, let's draw it out here again. I've got an A which is 10, and that's in the 16s. And then I've got a B which is 11 in the 1s. So I've got 160 plus 11, that's 171 in base 10. This also, I know we have been going at this for a while, so it's starting to sound a little rah, 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 rah. But I'm just about done. So here's an even cooler thing that I'll set you up with. Each one of these can be represented with a 4-bit pattern. So in 4 bits, so let's see, here's the hex, here's the 4-bit word. These are called words when they're 4 bits. So here it's 0, 0, 0, 0, 0, 0, 0, 1, and just write the binary numbers going on up. Or convert this number here to binary. So let's see, this is 2, 2, 0, 6 is 0, 0, 1, 1. And no, that is not 6. This is 6. This is 7. 1, 1. Oh shit, I'm getting really tired of writing those. You're probably getting even more tired of watching me do it. So what we do is we come over to our IEEE encoded bit pattern, and we group these by 4s. So to convert to hexadecimal, just look at the groups of 4 at a time and see what binary numbers represented. So this one's 3, so I put a 3 there for that. This one is, let's see, what do we got here? We've got an 8, a 4, and a 2, so that's 14. That's an E. That represents 14. This one here is, what is that? That is 6, so it's just 6. This is 3. This is 8. This guy here, what is this guy? This is, I'm sorry, what is it? E, thank you. Yeah, beautiful. Yeah, it's just 1 away from a full-on flush of 1s across. And then we've got this last one, that's a 3. And then finally 9. So, done, we did it. Let me summarize. The IEEE encoding of 1/9 in base 10 is you put a 0x, this indicates hex is about to follow, and then you write these patterns down, 3, E, 6, 3, 8, E, 3, 9. There you go. Done. Thank you, friends. Brent and I will get you added, my friend. Thanks for being here.
That was good.
And I'll be up here if you have any troubles. Please bring your laptops. Computer science folks, ever seen this anywhere? Kind of? Yeah.
They do it in computer architecture elective.
Oh, really? Oh, cool. Oh, so not everybody gets to see it. That's pretty advanced.
Now?
Sorry.